single phase uncontrolled rectifier. We've started with a single phase half wave rectifier. So to explain the operations, we always start with the or refer the supply voltage. So we have a positive half cycle here. This is known as a positive half cycle, and this is the negative half cycle. Yeah, positive half cycle, negative half cycle. So you also need to understand that the diode operates depending on the voltage and current of the circuit. It will only turn on when the voltage is forward bias, and we have the current that follow through the current that flows in the same direction of the diode symbol here, right? So that will turn on the diode. Okay, so for single phase half wave control rectifier, look at the positive half cycle. Okay, and because of that positive half cycle, diode experience the forward bias, and because this is a resistor, so the current start to flow clockwise, and therefore diode is on. So whenever diode is on, it will appear as a short circuit. Okay, it will appear as a short circuit, therefore connecting VDC to VS. So therefore output voltage we always refer to, equals to the supply voltage, and that's why the VDC here will copy the supply voltage here. It will just copy the supply voltage. And during negative half cycle, okay, during negative half cycle, the diode will be reverse bias, and the current start to flow in the opposite direction, anti-clockwise. Because this is a resistor, so current start to flow, but then because this is a reverse bias, then diode will be turned off. So it will appear as a open circuit. And therefore, there is no current flow. Therefore, the voltage drop across R will be 0. And that's why for the negative half cycle, you're going to see that the current and the voltage is 0. Okay, so just to give you some refreshment, and then we will always look into the average output voltage. So okay, always memorize the general equation. So to get the average value, you must integrate from 0 to t, the whole cycles, the function of the waveforms, and then you have to divide by t, yeah, the total period, one cycle. And then it's convenient for you to change to radian, therefore one cycle equals 2 pi, 0 to 2 pi VDC theta d theta, and then you get this equation, yeah, for output voltage and the rest. I hope you go back and go through this again, and please, I think I've shared with you through Padlet the PCB circuit. So try to beat yourself, try to construct the circuit through PCB yourself, and then just refer back to and just make a comparison with the one that I shared with you. So you must construct the circuit through PCB yourself, right? And then you can validate, you can verify the theoretical answer or the theoretical results from the equations that you have just now to verify your answers. Okay, then you have problem 1, problem 2. So again, look at this. You have calculate. This is actually to, when we have this sort of questions, then you know that you must perform the harmonic, the Fourier series. So try to get the Fourier harmonics, to get the harmonics of this waveform by using the Fourier analysis that we did just now. Based on the square waveform, try to when you understand that the steps, then you can apply here. So if you look at this waveform, I don't think it is a odd waveform. It is not even waveform. It is not odd waveform, and it is also not the half-wave symmetry. So you have to perform as a normal function, an, bn, integrate. Inshallah, you will get this answer, right? And compare with your PC. Okay, and then we go to the performance parameters. So look back. All this power factor, displacement factor, and the form factor. These two also important. Form factor as well as the ripple factor. This is less important. Distortion factor is important. Displacement factor is important, whereby the power factor, the actual power factor equation is actually this one. Okay, IS1 over IS cos B1 cos B1. The THD, total harmonic distortion, and the harmonics. So if you don't know the waveform, if you are given in terms of individual harmonics, you can find the RMS of the components by using this equation. Or else, if you are provided with the waveform and you can evaluate the waveform, the RMS can be actually it is more accurate if you use the equation the root mean square just now. Okay, let's proceed. And then we look into resistive and inductive load, whereby for resistive inductive load, you have a beta extension angle. You still remember that extension angle? So for this circuit, you have to remember we have this energy elements here stored the inductor. So inductor actually their behavior is the characteristic is stored some energy, and the current cannot change the direction instantaneously, okay, because of that stored energy. So therefore, just to refresh again, so during positive half cycle, right, so during the positive half cycle, the current will start to flow in this direction, and the voltage also forward bias, and therefore VDC equals to Vs. Sorry. So if you look at this waveform, VDC will copy the Vs, but only up to that point. Okay. When it crosses the negative into negative half cycles, the diode here actually reverse bias, because it's a negative voltage rate. But due to the current, if you look at further, the current is still flowing in this direction. In that direction, isn't it? The current is still flowing in that direction because you have the stored energy in your inductor. Therefore, it will causes the diode to stay on. It will remain turned on until this current is 0. Okay, so that's why if you look at this waveform, the currents, the voltage still copy the negative here. It still copy the negative area here until current equals to 0 at extinction angle. So when the current is 0, the diode will be open circuit, turn off, open circuits, and therefore voltage equals to 0 again. Be 0 again. Okay, so that is your waveform. So of course you're going to get a different output voltage, average, as well as the RMS. I hope I must emphasis on you complete the gap here. There is a missing solution calculations here, so please make sure that you fill in the gaps. Right? Don't just memorize the equation. So fill in the gaps. So the average output voltage will be that, and okay. And for the equations, I put here the detail on how to obtain the equation for the current. So you have a forced response circuit, the natural response circuit. Please go through. Inshallah, you'll be understand how it derived. And finally, you have this equation. In terms of theta, you have I theta equals to V peak over Z sine theta minus V plus V peak Z over Z sine V. So you use the equation and put in the value of theta and everything, so you can find, you can look for your beta, when you set this equation equals to 0. And please use the PCM again to verify the equation. I'm not sure whether we have started the resistive inductive back EMF. Okay, I think we stop at this particular point. Then we're going to continue with the next video. I think we stopped at before the back EMF 4.2.4. So next video will be continue. We're going to continue the lecture notes as for week after the actual lecture, after the break, after the MPKP. Okay, take a break and then we come back with a new video on the resistive inductive back EMF. Thank you.